Elastic potential, Day 3. Hooke's law. Hooke's law is a principle of physics that states that the force needed to extend or compress a spring. The law is named after 17th century British physicist Robert Hooke. F equals kx. Hooke's law focuses on forces. Generally, the constant, which is represented by k, is the amount of force required to stretch or compress a spring, coil, or bungee. Generally, these are objects which can compress or stretch and return back to their at-rest state or length. The x itself represents the difference between the stretched or compressed length in comparison to its original or at-rest length. The standard units for these values are newtons needed for each meter of compression or stretching, and finally meters for the change of length. Stiffer strings require additional force to compress or stretch in comparison to looser springs. General idea behind springs: the spring we focus on should be able to return to their original length without any permanent damage or warping of any kind. As noticed on the diagram to the right, the first spring is at rest. This is also known as equilibrium. This is usually considered to be the initial or natural length of the spring due to the fact there are no forces acting upon the spring at the current moment. The second spring is being stretched by an outside force or influence. This can be achieved in many ways, such as a vertical spring with a mass attached to the end, which allows the mass's weight to influence and stretch the spring. The third spring shown here is being compressed. When stretching a spring, we must take into consideration of the spring's constant. If you recall, the constant is the required amount of force to stretch or compress a spring for each respective meter. In this diagram, we view the same spring in three different stages or conditions. On the far left, we view the spring at equilibrium with no major forces acting upon it. If we attach an object with a mass of 1 kilogram, and stretch the spring an additional meter in length, we can say that the spring's constant is 9.8 newtons per meter. Then on the far right, we view the spring stretched an additional meter in length. It is safe to assume that the mass was double, with in turn doubled the force from weight. These three weapons, both in their primitive and modern designs, share the common element of elastic energy. For both the crossbow and the standard bow, they have bowstrings which are stretched when being loaded. Of course, this is not the only element which gives the arrow the force needed to launch. When it comes to slingshots, these elastic strings stretch, and are completely responsible for delivering the force needed to launch the projectile. With modern weapons, we have a similar design as the previous examples. The major difference is that the spring in this design is not intended to launch the projectile. These springs, or recoil springs, are designed to soften the reaction of the launch of the bullet. The recoil spring is being compressed instead of stretched. Traditional mattress utilize this type of springs. When you lay on your bed, you are applying your weight onto the springs, which compress and allow the mattress to conform to the shape of your body. Modern vehicles, and especially off-road vehicles, contain coils which serve as shock absorbers, which means when the road begins to become rough or unstable, these coils soften the felt impact. The combination of vehicle's weight, potential energy, and kinetic energy deliver enough force to compress the coils. Elastic potential energy, left white lenticular bracket PE, right white lenticular bracket, underscore equals 1, fraction slash 2 Kelvin x2, as stated prior. Elastic potential is a form of energy. As you should recall, energy's standard units of measurement are the joule. The K is the spring constant. This value is not the same for all springs. The units for this is newtons per meter. The stiffer the spring, the stronger the constant. The x is the change of length for the spring in meters. In mathematical terms, it doesn't matter if the spring is stretched or compressed, in other words in negative or positive value, due to the fact the value will be squared. The squared value will always return as a positive value.